Good morning, all of you. Today, can you hear me? I know that.
Yes, sir.
Oh, good. Today,
Yes, sir.
today, 24th June. I think 24th June. Yeah, 2022. So, welcome all the three batches manufacturing, mechatronics, and BST for today thermodynamics lesson. In the engines, turbines, okay, maybe gas turbines, internal combustion engines, steam engines. So you can see this thermal energy convert into mechanical work. Okay. So because of the combustion, lot of thermal energy is loaded, and then this thermal energy is converting to mechanical work. How do you know this very well? So I just put an animation as well here. This is the point. Even though this thermal energy convert into mechanical work, not all thermal energy is available for mechanical work. That's the point. So you have thermal energy, but this thermal energy availability is not to the fullest. Means not all thermal energy available, because you know that sometimes you feel that engines are very hot externally. Even sometimes, give me a second. So this is the issue with that. Not all thermal energy is available for mechanical work. So you have to see some practicality of this. Because if thermal energy, if you feel that engine is hot, means some thermal energy leak out to the surrounding. In some cases, we have to cool down the engines. Cool down means that we are taking some thermal energy out. So this thermal energy available for mechanical work, but we take it out. Yeah, so that's why not all available. One reason is the heat transfer. And the other is when the piston moves. So there are frictions, and this piston should move against the friction as well. So if there is friction, again, to overcome this friction, part of thermal energy being used. That's how. Friction issues, and sometimes, most of the time, the thermal energy losses through the surface walls in the cylinder. And also, there are a lot of random motion of the molecules, the energized molecules. Yeah. So they are moving elsewhere. Not all pushing the piston down. Some molecules move up, some moves down, some hit side walls and all. So you can see the piston is moving because that's the way for this energized gas to move or expand, and as a result, the piston moves down. But you can see this molecules moves randomly. Okay, that is a random. So that's also contribute for this unavailability of thermal energy, a portion really. So you have to listen very well, and you have to imagine this very well. Okay, you have to imagine this very well. Okay. So this thermal energy converting to mechanical work, not all thermal energy is available for mechanical work. You know this. So out of the total thermal energy, only a thermal energy portion available for mechanical work. The balance is the thermal energy portion unavailable for mechanical work. I just put that. Okay. So basically like that. Okay. For mechanical work. So that's why. So you need, other than the energy necessary for mechanical work, you need some extra as well. Because not all thermal energy is available for the converting, for the conversion to mechanical work. Quite general understanding, but it is important. So when you develop the solutions, when you outline the solutions, okay, the designing of the engines and all, to have a better fuel savings, of course, hybrid systems, it's different, but anyway, thermal energy converting to mechanical work, you have to minimize the unavailability of thermal energy for mechanical work, or you have to maximize the availability. That's why the technologists are doing those. Okay, technicians are doing the repairs and all, but the technologists, they will look into how to improve this efficiencies, minimize this unavailabilities. Those are the technological challenges. Even we can see some new engine solutions. You can see better performing in fuel, means for 1 liter maybe a better mileage. So quality of fuel, as well as this arrangement of the timely arrangement of this energizing and all, and the dimensions, the surface qualities, everything matter, even the combustion temperatures, pressures, and even the heat losses through the cylinders and all, reduce frictions, better lubrications, the long-lasting quality lubrication and all, even the vibration, minimize vibrations. A lot to consider when you need to look into the improvements. That is very important. It's a very important idea you should have, because not all thermal energy is available. That's a point. Yeah. So I put the topic here, entropy in thermal energy converting to mechanical work. It's the same thing, because entropy is a thermodynamic quantity representing the unavailability of a system's thermal energy for conversion into mechanical work. So unavailability of thermal energy. Give me a second, Putra. So unavailability of thermal energy. So that is important. So we have to minimize this. Yeah. So minimizing entropy and working with reduced or the minimum entropy is always very important. Okay, it's always very important. So here, when it comes to the engine, so mechanical work is done during the expansion. So you expansion, during the expansion, at the beginning, you may have certain unavailability of mechanical work in the thermal energy. That unavailability should not be increased. So that unavailability is the same during the expansion. We call it isentropy, constant entropy expansion. Yeah. Not changing of the entropy means whatever initial unavailability there, it is there till the end without increasing the unavailability. Without increasing the unavailability in the expansions. So that is very important. Okay. So it's good really. So we call this isentropic expansion. Yeah. So isentropic expansion. So you can imagine initially there is a certain unavailability of the thermal energy for mechanical work. So entropy represents that. If unavailability is not increasing, which means if the entropy is no change, we call this constant entropy or isentropic expansion. Even for engines, we can imagine this. For engines, for turbines, we can imagine this. And it is mostly an imagination. So imagination is one thing, reality is another. So we will see how to connect this imagination with the reality. Because this ideal case, we have to consider. Okay. Same for compressions. So suction and compression, this pump to a high pressure side, maybe even in the refrigerant compressors, maybe low pressure because of the suction, low temperature gas, compress to a higher level of pressures and send into the condenser. So in the compression also, so here what happens is when you compress, thermal energy is rising. Thermal energy is rising. Rising thermal energy has a potential to work. I mean, this rising thermal energy has a potential to convert that thermal energy into mechanical work. Yeah. So in that, again, if this thermal energy doesn't lose its availability, we call it isentropic compression. So not changing of the entropy. Okay. So the same entropy levels remain. Same entropy levels remain. thermal energy is building up, but the unavailability of thermal energy for this mechanical energy conversion or mechanical work, that unavailability is not increasing, or we call this isentropic compression. So again here, during the compression, if the heat losses there working against the friction and the disorderness of these molecules, and there should be a certain degree of disorderness. Yeah, all leads for the increasing of entropy. Means you have to do extra work to compensate for that entropy increase. Yeah, so isentropic compression is an ideal case where the entropy is not getting increased. Okay, so it's the same slide. Yeah. So isentropic compression and expansion is reversible and adiabatic process. So let me take this compression, sorry, expansion. I take the picture here, compression. Of course. Now you know that isentropic behind this. Isentropic means constant entropy, unchanging entropy. So unchanging entropy means this. This will not be changing. Unchanging. So when this is unchanging, the unavailability. So unavailability, see two portions. Available plus unavailable. Yes. So unavailability, because there is a certain portion. So we should control this unavailability. The availability is maintained at the maximum levels. Means that is not getting reduced in short term. Yes. Okay, good. So initially, there is a certain unavailability. So let's say here entropy level S1. Okay, entropy level S1. Okay, and let's say this expands until here. Maybe it expands until here. If you go for animation again, we can see. Yes. Entropy level S2. Good. And compression starts at the compression. Entropy level S1. In somewhere here. Entropy level S2. This is for your easy imaginations. So your unavailability of thermal energy portion for mechanical work remained, okay, if not changed. Okay. Yes. In general, okay, in general, in general, if you take S1 and S2, S2, you can see S2 is bigger. So this is the situation. So if I take S2 here first, S1 here, so S2 is greater than S1. So the final entropy level is an increase. This is non-isentropic. Isentropic. Okay, non-isentropic. Expansion or compression. So final entropy level is higher than the initial entropy. So that's reality. Okay, that's a reality. So S2 is S1. So if you take this for 1 kg, we call it specific. Whilst if it is biggest means for a given constant amount of mass or fixed amount of mass. Okay, let's okay. Now, put here is 2 is greater than S1. Okay. So unchanging, you can say S2 is equal to S1. Ideal case. Okay. An ideal case. So this is the real situation. Real cases like this. So the other case we will say ideal. Ideal means this is not real, is ideal. If can have, it is good. So we can try at least to make it closer to ideal. S2 is S1, ideal case. Yes. Okay. So, ideal. So ideal case. Real. Yes. Good. Real. So isentropic compression means ideal. Okay, ideal. So isentropic is ideal. Yeah, ideal entropy level. But this is real. Okay. I hope you will not get confused. Non-isentropic is real. This is ideal. Yes. Unchanging. So no thermal interactions. Go in, no out. It is not possible. Heat. Okay. Heat transfer. So transfer is consider no. Okay. Towards, but both cases it's outward, but I just put both arrows. Yes. So no heat transfer. No heat transfer. Nice. So no heat transfer we call adiabatic. Okay, no heat transfer means adiabatic. Later you can explore how these words came. Okay, adiabatic. So adiabatic means this compression and expansion. So those are thermodynamic processes. So these are adiabatic processes, thermodynamic processes. Okay. So here, this expansion, and here the compression. So compression is a thermodynamics process. Okay. The experienced by this working fluid. Expansion also the same. So adiabatic processes. So generally we no need to write this. Thermodynamics, yeah, all knows this. So adiabatic nature of processes. Okay, no heat transfer means. And one more thing here, when the same entropy levels maintain, the reversibility, I'm going to explain the reversibility now. Reversibility, let's say so this we consider as the state 1 before expansion. After expansion, this would be state 2. Okay. So 1 to 2 change is something gradually taken place. 1 to 2 change. One to two means you need some imagination here as well. So this is 1. This is 2. So there is a direction for this from 1 to 2. So one to two. One to two. So how do you know 1 and how do you know 2? Understand this, maybe the same mass here. So for the same mass 1 to 2, no change. And the 1, maybe your temperature, pressure, and the mass tells 1 what 1 means. So 1. So you have T1, P1. Okay. Actually, small p pressure. Okay. I'm having 1. Yes. True. Two. I'm a bit slow explaining here. One. So this is process 1 to 2. Okay. When this expands, process 1 to 2. Thermodynamic process 1 to 2. So we are going to study this irreversibility, what this means. One to two. For expansion here, you can see the pressure, that's a drop. Temperature, there is a drop. Okay. So you have the drops, but the M1 and M2 may be the same. So this is just an indication on even for the axis here, you can have the best axis here maybe hydro pressure. And here, even the volume maybe, the volume is increasing. No issues. P and V. Okay. Or even M. M is the same. M, no. Temperature. There can be, but let's say I put V1 as well. Small V1. Or even big V1 is okay. Small V1 for 1 kg. Big V1 for this given name. So you can have the parameters. So here, for the given mass, only 2 parameters is enough for the ideal line gas. At the temperature, pressure, or temperature. Volumes, specific volumes will do. Okay, that is a minimum number of parameters required is 2. So you will realize this when you do the calculations. 1 to 2. beginning, end. And there is a direction I just put here. Okay, later we will see. So reversibility means if for the same mass, for same two condition, if you are reversing this process, means piston moves this way, upward. So it follows the same path. So later you will see this. Follows the same path because 1 to 2 is, you feel that it's taken place all of a sudden, but yeah, irrespective of the time factor, if the process, if you imagine the change, a gradual change, so 1 to 2 change, if you reverse it, it follows from 2 to 1 exactly. So this is we call reversibility. So reversibility is this. Okay. The same one, reversibility, I will go for the compressions. Some imaginations. Later you can look into the definitions. Don't worry. So I will take this. Compression. Put it here. 1 is here. 2 is here. Yeah. So this is getting compressed. So higher pressure values, smaller volume values. So if you think of pressure scale, and the volume scale, pressure axis and volume axis as two parameters, you can see. For this case, 2 is something like here. 1 is something like here. So process 1 to 2. 1 to 2. And reversibility is 2 to 1. Okay. So we call this the path of the process. Okay, this is the path. Showing the change of properties. Showing the change of properties or parameters. O state, we call state. Showing the change of properties or parameters, O state. So this is the main word we are using, changing the state. Okay. Interesting. So there is a forward. And also there is a reverse. Okay. It's a path, that's why. So forward path, 1 to 2. And when you reverse it, start from 2, it exactly comes from to 1 using the same 2 to 1. If this is reversible, interesting. Okay. So this pressure, temperature, volume, mass, these are state variables. So the parameters. So S1, example, state. So I take the word state. Let's say state 1. So it's together representing your temperature. Yeah. Actually, pressure and temperature is enough. Okay. Pressure and temperature, P1, sorry, 2 is enough. Let's say V1 is enough for the ideal nature of gases. So even you can write, that's all right. You can put even all here. T1, no harm because it makes you understand M1. State 2, so you have the similar one. Okay, all represent. So P2, V2, T2, P2, V2, M2. I put all, don't worry, yeah? That's all right as long as you are understanding this. And for the reversibility, it is very important. It's a practical point of view. For the reversibility, this M1 is M2. Okay, it's showing the change of properties or reversibility. Process 1 to 2 and process 2 to 1 is a reverse, is a reverse of each other. Okay. So forward path, reverse path. Okay, falling on the same process line. Okay, falling on the same process line. So path. So path 1 to 2 and path 2 to 1. Process 1 to 2. Process path, or even process 1 to 2. And process 2 to 1. So process 2 to 1 is the reversal of process 1 to 2. Same. Okay. Reversibility. So in the reversibility, it is very important to notice that M1 is M2. For the practical point of view, constant masses, M1 is M2. And the other is path 2 to 1 is the reversal of path 1 to 2. If you in between 1 to 2, at any point here, because this line contains small dots, all connected becomes a line, and each and every point represent a state. Okay, state S. Okay, so state change from 1 to 2. So reverse path 2 to 1. The reversal of path 1 to 2. If possible, then path 1 to 2 representing process, thermodynamics process 1 to 2. Is a reversible process. Yeah, that's the point. Okay, that's the point. If path 2 to 1 is the reversal of path 1 to 2. Okay, and if possible, then path 1 to 2 representing process 1 to 2 is a reversible process. And there, it is very important for such processes. It is very important for M1 being M2. Okay, it's a practical point I just put here. Okay, but defining a reversible process, you no need to mention M1 as M2. So this much is enough. Okay. So in such process in general, M1 is M2. Okay. It's a closed, not to say closed system, even open systems possible. We can imagine the reversibility. So this is the reversibility. So the point is, if the entropy level at 1 and 2 are the same, okay, if entropy level at 1 and 2 are the same, we have to consider the process is reversible. Means no frictions, no heat transfers, no frictions, and adiabatic. Okay, so that's the point. Okay, so I will take the reversibility is here, and the adiabatic nature is here, isentropic. So reversible and adiabatic process. And we talk here about the reversibility. So this is expansion. So you have to go through some literature and try to understand. Yes. Too small PV, but it's okay. So this is for reversibility in expansion. You can see the engine. Reversibility in expansion. because you can see in the expansion, the volume is increased. So 1 to 2, you can see the V-axis. So this path moves towards the increasing of V. So when volume increase during the expansion, of course, the pressure reduces. Yeah, that's the way. And M1 is M2. Those are the practical tips. It's very important. So, reversibility in expansion. So you will see it here. Here, reversibility in compression. Reversibility in compression. Okay. Interesting. So this is isentropic compression and expansion, but here it is expansion. Here it is compression. Reversibility is a must. Okay. So yes. Then the next one. Yes, expansion, isentropy. So I will add the no heat transfer. Adiabatic. No heat transfer. So no heat transfer is adiabatic. So reversibility and adiabatic. So both combined, we call reversible adiabatic. So reversibility is here. I will take this here. Reversibility and expansion. And adiabatic nature here. So reversible adiabatic. Combinedly, we call this isentropic. Yes. Reversible and adiabatic. Isentropic expansion. Good. Reversible and adiabatic. Yeah, I leave this here. It's okay. Then I will go for the isentropic compression. So again, you have the reversibility. In expansion, sorry, here should be compression. Okay, I made a mistake here. Reversibility in compression. This slide also in compression. Reversibility in compression. Also, we have the adiabatic nature. adiabatic nature here. No heat transfer. No to heat transfer. Okay. No to heat transfer means adiabatic. And you have the reversibility in compression. Plus the adiabatic together make this isentropic compression. Okay. Interesting. And this one also we can turn maybe. Yes. So reversibility and adiabatic together is isentropic. So here it is very important to have some not just to say imaginations, but some possibilities of affecting the reversibility, because friction affects the reversibility. Even heat transfer also affects the reversibility. So no heat transfer is adiabatic, and we use the word reversibility again. So reversible and adiabatic. Okay. So here it's a compression. Okay, isentropic compression. Isentropic expansion. Yeah. Okay, good. So, ideal process. So your S1 is same as S2. So you have, even you can have your S values here. S2. Small or big, no issue. This one. So S1 is S2. For reversible, and adiabatic. S1 is S2. S2 means unchanged, what we call constant entropy, or we call this isentropy. isentropic, but for this case, it is compression. Okay. Isentropic compression. Expansion also. Same, but this is expansion. So look into your, I think, imagination. You have to imagine how this ideal process of reversible adiabatic. How can this be imagined? Okay. What are the phenomena related? Just get some understanding. Okay. It's very nice. 2 and it's 2 here. Just put this 2. And 1, this one. Yeah, good. So the process 1 to 2, the reversible nature and the adiabatic nature combined. See, this circle means combined. Jointly make this process isentropic, means constant entropy, means the unavailability of thermal energy. Okay. To convert into mechanical energy, that unavailability, there is no increase. Okay. It maintains. If non-isentropic, this increase. Okay. Non-isentropic, this increase. Okay, good. Further understanding of entropy. So further understanding in the sense, so comparing real with ideal. Okay, comparing real with ideal. So example in expansion, expansion. Here you can see expansion. So ideal is isentropic. Expansion. And real is the actual expansion. Okay, actual expansion. So here, the measurable one, generally, of course, entropy can be measured, but here, the what's the bottom line is the actual work done. Yes, work done. So this is important. Work done. Actual means real. Okay. So I use the word real. So here, ideal, we call ideal law, let's see, isentropic. Work done. Of course, in the expansion. Okay, this working fluid or energized gas. So expansion of energized gas or vapor or whatever we call it, working fluid. Yeah. So in this expansion, the thermal energy converts to work done, okay, or mechanical work done. Work done. So ideal and real case. So ideal isentropic we call W isentropic work done. Okay, isentropic expansion. No work done. Okay. In expansion, the work is done. Okay. W isen. Work done through isentropic expansion. So work done through actual expansion. Actual expansion. Real work done. So this is W real. So in expansion, W ideal or isentropic is more. W real is less. So here we are taking a ratio. Okay, a ratio of W real against the ideal. Means W isen. So this is a kind of indication that how closer this actual work to the ideal work, the isentropic work we are expecting. Okay, so if you take this one, this two, You really know that W real is lesser than W ideal or isentropic. Yes, that's true. It is lesser, but how closer is the point? Okay, how closer? How closer? Very close to ideal? Yes, it is better. So the point of interest is not this, but to know how close real to ideal. That's the point, important thing. How close the real to ideal. Ideal means isentropic. So that is the importance. How close? That's why how closer means we are using the word efficiency as a ratio, real to ideal. Okay. And if you multiply this by 100, this is a percentage. Okay. This is a percentage. We call this efficiency. Special name, isentropic efficiency. Efficiency. Okay. Isentropic efficiency. Yes. And this one, we use a symbol. For efficiency, we call neta. I see. Neta isentropic. Neta isentropic. I think small device sometimes you are using for your convenience, and you can see the small letters but still may be visible. So the shortened term is neta isen. Isen, we put this as a subscript. Subscript. Yes. Yeah. Okay, good. So this is for the expansions. Expansion means work done is here. Isentropic efficiency. In expansion, the same way. Now this is for expansion, entropy. So here it's for expansion. Means work done, turbine, engines. Now let's see compression. What happens? In the case of compression, okay, thermal energy is adding by a mechanical work done. Okay, you're turning this. See, you're turning this. So thermal energy is adding by mechanical work done. Okay. So work done. So work done. Okay. Through isentropic compression. So not to say through work done in. So work input here. Okay. Work input. Okay. Through isentropic compression. So isentropic work in compression. Okay. Let's say WISEN. Okay. WISEN, isentropic work of compression. Then real. So work done. Okay. So work input. Through actual compression. means the real work input. Okay, W real. So here for compression, it is different because you are compressing, you are doing work on the compression. So W real is more than WIC for compression. Okay, remember this. For expansion, W real is less than WIC. Here W real is more. So we want to minimize the real. So how closer the real to the ideal is the case. So isentropic efficiency in compression is now change. W isentropic to W real times 100%. See now it's different because it's compression. So, need isentropic compression. So W isen to W real. See, it's change. W real times 100%. So need isen compression is W isentropic against W real. Yeah, so very important. How close W real to W isentropic? Oh, ideal. That is very important. How close are this to the ideal case? The ideal is the best case here. So always reduced entropy. It is very important. Okay, reduced entropy. It is extremely important. Okay, reduced entropy. In compression, in expansions. Compression may be refrigerant compression or air compression. Expansion may be an engine, turbine, gas turbines, steam turbines, gas-powered engines, and vapor-powered engines. So this isentropic is a very, how to say, is a very important concept. It's related with entropy. So your sense of understanding of entropy is making you feel good about learning thermodynamics. Okay, it's quite interesting. So I believe I have explained this in much simplified manner, and we will go for a small question now. Okay. Small question. So this title, Further Understanding of Entropy, Comparing Real with Ideal for Compression Process. So you have to have understanding of all. Okay. and the technicalities behind this. Okay. It's very interesting. We together developed this wonderful slides. Okay. See how nice. Okay. We have a student request here to do a physical session to make this understand further. Hmm. Definitely, we will go for a physical session. Maybe after this 2 weeks, but after this week, because university mostly running online. So there are requests for online, but we will try to understand this and we will try for that. Yeah. So you have to really think about this. So that is the situation. So we will try to have some physical classes, but don't wait for the physical class, Putta. Give me a second, Buddha. This is from the previous exam. Can you note down this, Putala? You managed to note down?
Excuse me, sir. The
Ah,
mic is open.
yes, mic is muted. Thank you, Buddha. Now we will see how to understand this. Okay. The compression processes. Slowly, we will see how to understand this. So, so when you see a question, there is a way of imagining this. So in the compression process, at least you have some understanding of this, what's taken place. And you have 1 and 2. Now this 1 to 2 is the process. Even here you can see 1 and 2. See, 1 to 2. So this is a real one. Okay. So I take this out. 1 to 2. Okay. The compression process. Here you can see the compression process. See. So reversibility, you have idea, but here the compression process is this compression process. One to two. So you must have understanding of this, basically. Yeah. So 1 to 2, 1 and 2. So S1 is S2 for isentropic. See, S1 is S2, unchanged. Okay, S1 and S2 unchanged. That's why now for compression, since S1 and S2 unchanged, so S can be one axis, and here it's mentioned the enthalpy, specific enthalpy for, which means for 1 kg. So 1 to 2, straight up is the isentropic compression, you can see here. But real S2 is greater than S1. So see the deviation, real compression. Okay. This is ideal one. This is only P and V. Later I will draw the TS. So real one. So your entropy is increasing from 1 to 2. Not like S1 equals S2. Okay, not like S1 equals S2. So there is an increase. So work done in compression. Okay, compression work input here. See enthalpy axis here. You know from previous lessons. Okay, previous lessons. W, see, even isentropic we have introduced. See, W is the enthalpy difference here. W, see, enthalpy differences for compressions in the previous sessions. So W is enthalpy differences. So H2 minus H1. So you have W H2 minus H1 for isentropic. Okay. Here it is called WS. Okay. And real is this H2 real minus H1. See. So W H2 real minus H1 is W real. W isentropic we call WS is H2S minus H1, because W is H2 minus H1. Okay. So the efficiencies we have explained, W isentropic divided by W real. See, isentropic is WS. by W real. So this data all given. So asking the real compression work input is quite simple. Okay. But there should be some very good understanding. So if we work on this, so W is H2 minus H1. Okay, W for 1 kg. It's H2 minus H1. Okay, good. And this is in general. And let's say now isentropic. Equal WS in this. So WS S is H2S minus H1. So W real. So W real is H2 real minus H1. Okay. W real. So even REAL. And WS here. So H1 compression starts at 1. Okay, 1. Starts at 1. So this case is 1. S2. I just put it. For isentropic S1 is S2 If not, S2 is more than S1 because entropy is increasing. Okay. Non-isentropic S2 is greater than S1. I mentioned that. See, the W real, okay? The S2 is greater than S1 also. I did mention that because entropy is rising, if not unchanged. So your case is here, H2S minus H1, W real is H2R minus H1. So the compression, okay? You can look for this. See, neat Isen compression. See. W isentropic divided by W real. $35 kilojoule per kilogram. This is 35 kilojoule per kilogram. Okay, kilojoules per kilogram. See, divided by W real times 100. So efficiency is here 0.9. Okay, so this one in the designs, somehow they can get this efficiency is 0.9. So 0.9 means this is 90, okay? Efficiency is 0.9 means this is 90. Or the ratio. So you can write this as 90 or you can write the same thing if it is 0.9, this is 0.9, then you take this 100% out. Okay, 0.9 is 90%. Okay, that is or this. You can take the W real value from this. So W real is more than 35. So you can write it. W real is 35 kilojoule per kilogram divided by 0.9. See how simple. So you will have a value for this. 35 kilojoule per kilogram divided by 0.9. So if you understand this compression and the isentropic nature, the ideal nature of compression, now it is quite easy. Okay. So it is not about getting the answer, but understanding this. So this is 38.9. See. So you should know why. This is more because Real is more than the ideal or isentropic work in compression. Unit kilojoule per kilogram. Kilojoule per kilogram. So this is the answer. Okay. See. Quite simple. Okay, understanding is very important. And if you look into the other example, question is another question. Give two suggestions to reduce the reversibility in compressors, reciprocating compressors. So I'm sharing this. So give two suggestions. So this is we call understanding technology. So if you are going for this, reciprocating compressors are this. You know about this in general. The compressors with the moving pistons. So you can give two suggestions how to have the less heat transfers, less frictions and all. Some suggestions, okay? It's based on your thinking approach. Further down, expansion. See? Expansion. You can mark this. Okay. Real expansion and isentropic expansion of power generation processes are shown in below, because 3 to 4 expansion. Let's say expansion of an engine. Engine can generate power by driving a generator, let's say, or a turbine. Okay. So you have the state 3 and 4. That's why you have one-time note, and also you should attend the lectures. You have to follow the videos. Okay. That is very important. Okay, that is very important. So we'll go for the next one. It's to understand the same like this compression. Okay, sorry, expansion here. Expansion. So again, you can see you come with your imaginations, expansions, and you have the efficiencies. So this is 3 and 4. 3 and 4. One to two is this way, bottom to top, compression. So when it comes to expansion, later we are going to learn about this. So 3 and 4. 3, where this expansion or the work done starts at 4. It ends, means the exhaust opens. And somehow it's designed in this way. So 3 to 4. Same way here, compressions. we will look for the expansions. Three to four. It's not about the reversibility. Three to four. Okay. T4. Sorry, T3. P3. P3. And actually M3 is M4. T2. So 3 to 4 here. Expansion. T4. P4. P4. M4 is equal to M3. Okay. So that one you should understand. Okay. M4 is equal to M3. So this constant mass undergoes the expansion and the work is done. So basically you have to have this understanding. If know this understanding, you cannot take that question. Okay. So your S3 values is 3. And here is 4. Okay. Big values, no issue. So even if not isentropic or ideal, then S4 is more than S3. That's why. So here S4 is more than S3. Later I will draw that diagram. So same way here, we can look into the analysis now for that question. I will take this question, take this slide. The same way. So you have the isentropic and you have the actual case. So you should know what this. See, I will take this. This is the one, isentropic efficiency. So here you can see. See, real expansion. Less work, that's why. Actual is more work done. Ideal one, okay? Actual one is less. That's why W real divided by W isentropic. So here, if you are looking into the same, This is 0.9. 0.9. See, it is 0.9. And here, so WS is the isentropic work done. And W real is here. So if 0.9 is not a percentage, you can take this out. Okay. Then from this, W real is real work done. Yeah, W real is here. Is 0.9 times W isentropic. W isen is given as WS. Okay, WS. So this is the expression. W real, if you can take again, this. Yeah, good. And let's draw this diagram now. Okay, because you know that the new slide, take this out. Same like here. W real is in this case for the expansions initially high value and H4 change real. So W isentropic is H3 minus here it is 4 but isentropic. Okay. And 3 and 4, you can see at H3, higher pressure values, H4, low pressure values. And this HS diagram, if we draw it, separate, because this expression say that H and S are important. Okay. Give me a sec. Okay. Generally for work done in expansion, if you take S3 and S4, S3, let's say the smaller value specific per kg, and your S4 is for real, okay? So S4 real is always means during the expansion, this entropy increases. Now you have to drill what entropy means we have discussed today. Okay. Later we will try to calculate these 4 values, don't worry. Yeah? So here one axis is S. The unit I think in the steam tables, we learn about this. Entropy as a calculated property. You have learned. It's a very important property. S. S-axis. Okay. And because of this, work can be seen as the differences in enthalpies. We have learned about this. Differences in enthalpies in the previous sessions. So another axis we will take here, enthalpy. Kilojoule per kilogram as the unit. So 3.3 should be known. At the higher pressures, sorry. Your P1 and P2. P here is P3 and P4. The constant pressure lines. P3. P4. And then this is H-axis, this is S-axis. So you mark your 0.3. Is you can mark somewhere here. Then the isentropic expansions, this straight away comes down. No change of entropy. Like this. So for isentropy, use S. 4S is here. And really something like this. Starts with the same point. This real. H. So this is real. 4R. So in technology, we should try to bring this as closer to this. That is where the technology, the secrets are. Okay? The technology, the secrets are. Yes. So for real becomes 4s, it is isentropic, but getting closer is better. So for this case, this has efficiency of 0.9. So you have a real divided by the ideal. Okay. That is divided by H3 minus H4. This is we call efficiency. Neta. Isentropic. Neta isen. Axis. H-axis. Okay. So high pressure, P3, to reduce pressure during expansion. Entropy unchanging is isentropic. Entropy changing, of course, it's increasing. It's the same. Okay. Even the expression is given. Okay, even the expression is given. So quite simple. Same way for the compression. You can have a similar curve. So this is HS4 expansion. Okay. This is for gases. For vapor, we use TS. There also you can get the H values, which is for gases. HS. Anyway, I take the gases out here. Yeah, you can see the constant pressure lines. These are pressure lines. So we have to study these behaviors as well. Okay. It's just for compression. HS curves. So 1 to 2. So S2 real is greater than S2. Entropy increases. So this is pressure is rising from 1 to 2, pressure being raised. So 2 is here. This curve the other way. One to 2. So this is 1. This is 2s. Okay. Entropy increases in the real. So 2 real is this. Okay. So the now this is the effect, bringing 2 real as much as towards the 2s. There the technology works. So Ws is H2 minus H1. This is H2s. So need Isen. Ws is a lesser value. W real is bigger value for compression. So this is compression. So Ws is H2s minus H1. W real is H2 real minus H1. Okay, good. So try to understand. This one is quite easy if you follow the previous lectures, notes, and your one-time notes. These are quite easy, even though we are learning online. Okay. Good. So this is one of the questions you got for the previous exams. A few more here. But you can see the isentropic nature, expansion, and compression we have learned. Real expansion and isentropic expansion. Explain why isentropic expansion, see, reversible adiabatic. It's isentropic is not real in steam turbine applications. Why it is not real? That's why you have the isentropic efficiencies. Drawing TS diagrams. Next week, we will do the TS diagrams for the power cycles. So you can see this nature of questions even in the coming exams. It is quite easy, but you should understand. So let me give some questions to you as continuous assessment. Even this will be one of the continuous assessments. So if you understand this, you can answer very well. Okay, understanding thermodynamics that is what I'm expecting. Even we have done this one. Same things are coming for the exams. Even this time also the same. See? Can you remember this in our notes? Notes, we have done the same. See? Our analysis. Yeah, good. That's why these notes are focusing on supporting your understanding. Okay, so you have to look into this, how to have a good understanding on this nature of subject. Okay. Thermodynamics is, as I say, is quite useful. Okay, quite useful, and you will see its applications are really remarkable. It will bring you a lot of opportunities. But when it comes to the basic concepts, most things you will not see. Physically, you will see the engine, you will see a refrigerator, you will see a boiler, but seeing it thermodynamically, you have to have a different eye. Okay, different eye. You have to see through the brains and minds. Yeah. That is very important. Understanding is the key for being successful in this subject. Actually, if we can join physically, it is very nice. But we have issues. Even today happened to be a holiday for the universities and all the government sector. So today even our university is closed. No one there, if I'm not mistaken. Okay, no one there because it's a holiday and it's Friday. So we have to manage this. So let me send you some courseworks, but make sure your daily notes and one-time note combinedly, you have to understand. This is what we call the understanding the science and technology in thermodynamics. Okay, it is very important. These are more than the words. Okay, very important. So today, whole 4 hours we spend on this because it takes time. Okay, so 12:35. So we will wind up the class today. Before winding up, give me a second. You must have a feeling on this. Thermal energy converting to mechanical. There comes the entropy and all. Because not all thermal energy is available for mechanical work. So portion is available, portion is unavailable. Our concern is with the unavailable energy. That should be minimum. And we should not let this unavailable energy portion increase during the process, means we should minimize this entropy rise. Unless we make it 0, that is isentropic. If not, we have to minimize this rise. Means keep the isentropic efficiency to the maximum possible. Theoretical maximum is 1. Isentropic expansion. Yeah. Not changing of the entropy. Not changing of the entropy, even for compression. Then all the thermodynamic interactions are purely for the mechanical work done. Okay. And even compression, the mechanical work done is there to make it thermodynamically energized. Again, in the expansion, it is thermal energy to work. Here from work to thermal energy. So any unavailability of thermal energy for work. And also if work creates some energy unavailability for the thermodynamics processes, thermal processes, that's also not good. And all related to this entropy. So entropy. So non-isentropic S2 is greater than S1. Okay. So 1 and 2. If isentropic, S2 is S1. So how to make it reaching at least this ideal, this adiabatic and the reversibility. We have learned a little about reversibility as well. And combining all this reversible adiabatic is to achieve the isentropic nature. But 100% means 100% isentropic efficient is ideal case, but we can have at least over 90% of the efficiencies in compressors and all. Okay, good. So nice. Try to understand this. I'm sending you this note. So comparing real with ideal expansion. Isentropic efficiency in expansion. So isentropic expansion is more, real expansion work is less. So the ratio as a percentage is interesting. This for the compression, a similar one. So isentropic compression value is less because we are putting work in. So real is more. The ratio again less than 1. Or efficiency is less than 100%. Question. Question is the answer really. Compression process. Another expansion. Question. You will get the answers. Here the WS is not given, so 0.9 times WS. So the real work done is less. But for compressors, real work in is more. HS for expansion. Expansion means work done. HS for compression. So that's all for today. I hope you understand something. Up to certain levels, and you have to further look into this. Then you will have a better understanding. So let me save this slide. Save as PDF. So I will send this to you afterward, and also I will share with you the video file, but I'm experiencing a huge size of video file, sometimes closer to 1 GB. I don't know why. That's why I couldn't share the file. So let me try anyway. We will see how this would be today. Thanks, Puta. That's all. So let me email this to you. So keep going, learning. Yeah, that's why it is tough, and you have to be consistent. Thanks, Puta. Okay, take care, all of you. Bye then. Bye.
Thank you.
Okay. Then.